Hey guys, welcome to our presentation on a lumped electrothermal model for a battery module with a novel hybrid cooling system. Myself Suman, I've been taking care of the ANSYS simulation for steady state part, and Arturo Montes has performed ANSYS simulation for transient state, and Santos Mono has did the MATLAB coding. And here is a summary of our presentation while we're going through this presentation. And the first one is why, how, and conclusion, later on transient state analysis, then comes the steady state analysis, later on MATLAB coding, and in the end, we're going to do the conclusion. And the why part, actually the battery module, when the temperature increases, when the energy gets discharged, there will be a temperature increase, which in the later on can cause the explosion, which can cause major issues. And how, actually they performed a MATLAB results and 3D model simulation for comparing the results between the CFD models and the MATLAB results. In the conclusion, they compared that the one-dimensional model was successful in getting the temperature, and there was only slight difference in the percentage compared to the voltage and temperature of only 1% in the voltage and 4.5% in the temperature, which is negligible.
As far as the model is concerned, we see the full model, which includes 12 battery modules. In our simulation, we're working with a quarter part of that model due to the symmetry of along the longitudinal middle axis of the battery module and on the transverse direction of the battery module. So you can see that quarter section is representative of the entire battery module as far as the effects of cooling. For the mesh, we use separate materials. We have 2 PCM embedded within the cooling plate, cooling channels inside, and 2 batteries. As far as the inlet, we have 1 inlet and the 3 outlets, which represent the cooling channels. When we look at the transient results, when we look at the temperature and positions, there's a couple things going on. The cooling plate boundaries, you can see the temperature distribution from the bottom to the top of the plate, where you see the bottom PCM and top PCM material. You see that at the middle of the PCM material, it has the highest temperature, meaning that the energy dissipated is uniform in both directions. And at the center, it's maintained its temperature, meaning that the cooling boundaries are dissipating the heat from the PCM material. When we look at the cooling plate performance versus fluid velocity, we examine the effects of different velocities on the temperature gradient of the cooling plate. So you can see clearly that by having a larger velocity for the fluid, it increases the temperature gradient versus having a 1 meter per second or low velocity, whereas you only dissipate 2 degrees over a period of 25 seconds, and that compared to our theoretical values, our calculated value is 8.3 meters per second, which stabilizes near and close to the theoretical experimental value.
Well, in the steady state analysis, as we can see, the y-axis represents the temperature and the x-axis represents temperature distribution across the vertical axis of the plate from bottom to top. And we performed the 3 different velocities for getting the temperature, and we compared with the theoretical value for our research paper. As you can see on the left page of the side, that there are 2 velocities, one for the 8.3 meter per second and other for 16.6 meter per second. When as you can see that when the temperature is lowered for 8.3, that there is a slight increase in the temperature at 0.05 millimeter for all the theoretical and 2 different values of velocity at 20 degree Celsius, as compared to, you can see the right corner of the page where the temperature start decreasing in the ANSYS result, and comparing with that with theoretical module, the temperature increase at 50 degree, temperature start decreasing at 50 and it's gonna rise till maximum reaches the 30 degrees Celsius in the theoretical, but in our value it's gonna start rising till the 27 degrees Celsius, and it's gonna keep dropping after that.
Right, for the MATLAB results in comparison, the top 5 figures are the graphs produced from the research paper. They use an energy balance of the battery, where the energy stored is equal to the heat generation from the battery subtracted from the conduction of the thermal interface material and the natural convection within the battery itself. From those graphs, I was able to get the total change in temperature of the battery. In doing so, the heat generated from each cell. For the ANSYS comparison, the simulation produced the temperature profile from bottom to top of the plate and the change in temperature with respect to time. Using those values, I was able to create a MATLAB code to calculate the heat generation of the cooling plate using the equation shown.
Well, as far as conclusion, overall, the giving consider all the constant and parameters, we are able to see the general trend showing up in the both steady state, transient state. It's going to compare the research paper, and also when the MATLAB code is compared with the ANSYS result, it's almost semi-correct and compared to research papers. So, well, the slight error is caused because we use the quarter section of the module, and there might be different changes in the building of the module. Yeah, thank you.